last lesson, we discussed the EPR paradox. We found out that the conception of hidden variables suggested by the authors of paradox is contrary to quantum mechanics. And now we are ready to find out whether one has to describe the physical reality using the hidden variables, or one has to use the quantum mechanics to describe events in the micro world. John Bell suggested an idea of an experiment that allows one to check the correctness of both theories. Today, different variations of this experiment exist, and all of them are being called the Bell Inequalities test. However, John Bell had nothing to do with these experiments. We consider the Bell inequalities in form suggested by Clauser, Horner, Shimony, and Holt. These inequalities are also referred to as C*S* inequalities, named after their authors. However, for simplicity, we will just call them Bell inequalities. Consider a quantum system A plus B being composed of two subsystems A and B. Let A and LA prime be the observables of system A and MB prime be the observables of system B. Consider a simple spectrum for each observable with only two eigenvalues of +1 and -1. In other words, if one measures any of these observables, one will obtain plus or -1. Going forward, know that we will be interested in a certain observable S corresponding to the whole system A plus B. Going through all possible values of observables of A and B subsystems, we will get the limits for the value of S. This means that we will find the maximal possible value of S and the minimal possible value for S. So, if we assume Einstein's position and consider all four observables to be the elements of a physical reality together, i.e. the values exist even though our rough instruments don't allow us to measure them, then there exists an arbitrary set of observables values, i.e. a set of their spectrum's values. For example, there exists a set containing only the value of +1 for each observable. In another set, all four observables have a value of -1. A third set contains +1 value for observables LA and LA prime, while observables MB and MB prime have their values of -1. Denote these sets by L, I, A, L prime, J, A, M, K, B, and M prime, N, B. And I, G, K, N can take the values 1 or 2. So we have 16 of these sets in total. Here L, I, A are the possible values of the observable LA, LG prime A is the possible values of the observable LA prime, and so on. Let's construct for each set a value of an observable S that is a function of LA, LA prime, MB, and MB prime. For the set with indexes I, G, K, N, the value of S will be SIGKN equals LIA plus L prime GA multiplied by MKB plus minus LIA plus LG prime A multiplied by M and prime B. It can be shown that for any I, G, K, N, we have SIGKN, the magnitude is less or equal to. Suppose we don't know the state in which the A plus B system is. So, we don't know which values exactly take the observables LA, L prime A, MB, and M prime B. And therefore, we don't know the value of S. In other words, we don't know the indexes I, G, K, N. However, we are interested only in the average of S and its borders. Consider now a sample of n which is far greater than 1 different sets. We consider in fact an ensemble of identical quantum systems A plus B and perform here an ensemble averaging to find the borders of S, to find the borders of averaged S. So we have the magnitude of averaged S equals 1 over n sum over I, G, K, n S, I, G, K, n I, G, K, n. Here n I, G, K, n is the number of S, I, G, K, n in a sample of n values. Let's introduce the probability. Since the probability is, in fact, n I, G, K, n divided by n, we can rewrite it in the following way. Here we get the sum over I, G, K, n, S, I, G, K, n, and P, I, G, K, n, where P, I, G, K, n is the probability for S, I, G, K, n to appear after a measurement. Since the magnitude of S, I, G, K, n is less than or equal to 2, as we learned before, right here, we can write the following. This is less than or equal to 2 multiplied by the sum over I, G, K, n, P, I, G, K, n. And since this is the total probability, it equals 1. That's why this equals 2. So we now obtain the following. The magnitude of average S is less than or equal to 2. Wow! Now we can turn back to the definition of S and write the following thing. The magnitude of average S equals LA MB minus LA MB prime average plus LA prime MB and plus LA prime MB prime. And all of this is less than or equal to 2. This is exactly what we needed. So, we have introduced the quantity S that corresponds to a certain observable in composed A plus B system. We have shown that the hidden variables conception predicts that the magnitude of its average is less than 2. In order to show this, we had gone through all of possible values of observables LA, LA prime, and MB, MB prime, on which the quantity S depends. The inequality we obtained is the Bell inequality in the form suggested by Clauser, Horn, Shimony, and Holt. Now, our intention is to compare the obtained result for magnitude of the averaged S with the quantum mechanics prediction. To each pair of simultaneously unmeasurable observables LA and LA prime in subsystem A and MB, MB prime in subsystem B, assign the appropriate Hermitian operators. Since the observables related to the same subsystem are simultaneously unmeasurable, their operators do not commute. As far as the spectrum of these operators contains only +1 and -1, the squares of these operators in matrix representations will be equal to the unit matrix. Let us now identify an operator for the observable S. Since our observables LA, LA prime, MB, and MB prime only take values of plus and minus 1, they are called dichotomous. It's known that a square of a dichotomous operator equals an identity matrix. So we can write LA squared equals LA prime squared hat equals MB squared equals MB prime squared. And all of this equals identity matrix. We'll need this property soon. Introduce an operator S hat equals LA MB minus LA MB prime plus LA prime MB plus LA prime MB prime. In order to find the magnitude of averaged S, consider the following difference. 2 square root of 2, an identity matrix minus S, and we can rewrite it using the property achieved earlier. So 2 goes down and turns into the square root of 2. And here we got LA squared plus LA prime squared plus MB squared plus MB prime squared minus S. We can now use an explicit form of S and find a bit of algebra to obtain the following. 1 over square root of 2 LA prime minus MB plus MB prime divided by the square root of 2 to the 2 plus 1 divided by the square root of 2 LA minus MB prime over square root of 2. And this goes to the 2. Again, this is just an algebra. But what is essential that this is a sum of 2 squares. And that's why, after an averaging, assuming an arbitrary state of the A plus B system, we have the following. 0, 2 square roots of 2, an averaged identity matrix, minus S. Yes, and all of this is greater or equal 0. We see it because we got it at the left hand here, and here we got the sum of 2 squares. So the averaged identity matrix obviously equals 1. And that's why the averaged S is more than or equal to square roots of 2. Similarly, one could prove that the averaged S is more than or equal to 2 square roots of 2 minus 2 square roots of 2. And thus, the model of averaged S is less than or equal to 2. This is actually what we needed. We can now turn back to our definition of S and write the following. LA MB minus LA MB prime plus LA prime MB plus LA prime MB prime. And all this is less than or equal to 2 square root of 2. So we have found out that according to quantum theory, the magnitude of the averaged S is less than or equal to 2 times square root of 2. The estimation we obtained for S is called the Tyrrell-Sohn bound and named after Boris Semyonovich Tyrrell-Sohn, the one who derived it first. As we can see, the Tyrrell-Sohn bound is greater than the estimation obtained according to the hidden variables conception. Thus, if one obtained in experiment the value for S greater than 2 and less or equal to 2 times square root of 2, then the Bell inequalities are violated and the quantum theory predictions occur to be correct. Otherwise, if the absolute of averaged S is less than 2, then the Bell inequalities are obeyed and the hidden variables conception is true. Let us now consider an experiment similar to one set in France in 1976. We consider a pair of fermions A and B. In our experiment, the observables LA and LA prime correspond to a measurement of A fermion's double spin projection along vectors A and A prime. The observables MB and MB prime correspond to a measurement of B fermion's double spin projection along vectors B and B prime. For the case of fermions with a spin of 1/2, the spectrum of observables here includes only 2 values, plus and minus 1. In the case we consider, all vectors A prime, B and B prime lay in the ZXZ plane and they are different from each other. They are all different from each other. One way to choose these directions is to pick positive and negative directions of Z and X axes. These axes in our experiment correspond to the axes of 2 Stern-Gerlach instruments. Let's consider the singlet Bell state beta 1,1. That is 1 over the square root of 2, 0, 1, minus 1, 0. Let's take a direction A, which is sine theta A in half, 0, and cosine theta A in half. So the operator for the observable LA, that is the fermion spin, is LA with hat equals A multiplied by sigma A with hat. And this is, since we got our A direction, equals sigma 1A with hat sine theta A in half plus sigma 3A with hat cosine theta A in half. We can also get similar expressions for the observables LA prime, MB, and MB prime. And we have the magnitude of averaged S equals the following construction: LA hat MB hat minus LA MB prime plus LA prime MB and plus LA prime MB prime with hats. Let's mark this expression with a star. Consider now the following average separately. This one, beta 1,1, LA MB, beta 1,1. So just we want to see the average of this operator in the state beta 1, 1. And as can be seen, it equals minus cosine theta AB, where the theta AB is the angle between A and B vectors. The similar expressions can be obtained for any other term in the sum star. And finally, the model of averaged S can be rewritten in the following form. The model of averaged S equals cosine theta AB minus cosine theta AB prime plus cosine theta A prime B plus cosine theta A prime B prime. So now, suppose we have theta AB equal to theta A prime B equal to theta A prime B prime and equal to pi over 4. And theta A prime B, AB prime is equal to 3 pi over 4. Then this can be easily evaluated. And this will be equal to 2 square roots of 2. And what we got now? Actually, we have the magnitude of averaged S equals 2 square root of 2. And so the Tyrrell-Swan bound was reached. It means that the Bell inequalities are violated. So we have obtained the magnitude of average observable S value in explicit form. We see that it depends only on the angles between the vectors we measured spin projections along. These angles are theta AB, theta A prime B, theta AB prime, and theta A prime B prime, and they are depicted on the separate figure. If one chooses the directions so that the angles theta AB, theta A prime B, and theta A prime B prime are equal to p over 4, and the angle theta AB is equal to 3p over 4, then one reaches the Tyrrell-Swan bound for the absolute value of averaged S. Thus, the Bell inequalities are violated. This means that the result predicted by the hidden variables conception occur to be wrong. Instead, the results obtained from the quantum mechanics are consistent with the results of the experiment. The violation of the Bell inequalities and the Tyrrell-Swan bound reach demonstrate that non-local quantum correlation characteristics of the quantum entangled states contribute into the absolute value of the averaged S. We will point out the practical benefit of such correlation when discussing the superdense coding and quantum teleportation. However, before that, we will get ourselves familiar with the general principles of classical and quantum computations and consider the simplest logical operations. See you next time. Thank you for your attention.